In this video, we are going to talk about bounded sequences. So let's define mathematically what does it mean for a sequence to be bounded. Consider a sequence a sub n which always is less than or equal to some number, let's call it capital M. In this case, we call the sequence a sub n is bounded above, which means that this number m is act like a ceiling for this sequence. In other words, the terms of the sequence never goes up higher than this value, which we called it m. A graphical representation of this definition would be something like this. You can see an increasing sequence here, which means that each term in a sequence is greater than or equal to the previous one. But as you see, none of the value of this sequence goes higher than this number. So we can say that this sequence is bounded above by m. Now that we have learned what does it mean for a sequence to be bounded above, let's consider the second case, which is bounded below sequence. Consider a sequence a sub n, which is always greater than or equal to some number, let's call it capital N. In this case, we call the sequence bounded below, which means that none of the terms of the sequence never go below this value, which we call it n. So the n here is acting like a floor for a sequence. Now let's consider an example for each cases. Let's say that h sub n is equal to n divided by n plus 1. We know that if we plug in the n equal 1 to this sequence, the first term is equal to 1 over 2. The second term is 2 divided by 3. And the third term is equal to 3 divided by 4. If we calculate the decimal value for each number, here we have 0.5. The value for the a sub 2 is 0.66, and the third term is equal to 0.75. We can see that this sequence is an increasing sequence because as n grows, each term is bigger than the previous one. But if we take the limit from this sequence as n approaches infinity, we know that the limit for this sequence is equal to 1, which means that if we plot the sequence in the Cartesian plane, the sequence goes up, but it never goes above the 1, because the limit for the sequence is 1 and the value of the sequence is getting closer to the 1, but they never touch the 1. As a result, this sequence is always less than or equal to 1. So we can call this sequence a bounded above sequence. For a bounded below sequence, let's define another example, which is a sub n is equal to 1 over n to the power of 5. Let's first calculate whether the sequence is monotonically increasing or decreasing. We have learned from our previous video that if we take the derivative from a function and this derivative is greater than 0, so we have an increasing function. If the derivative is less than 0, it's a decreasing function. So let's take the derivative of this sequence. We can rewrite the a sub n to the form of n to the power of -5. Since the sequences are not differentiable, we should take the derivative from the continuous function. The continuous function related to this sequence is f of x is equal to x to the power of -5. By using the power rule, the first derivative for this function is equal to -5 times x to the power of -6, which is equal to -5 over x to the power of 6, which is always negative. So we have a decreasing sequence. If we plug in the n for our sequence, we are going to get a positive result. Whenever you have a function that is always positive, the lowest value that it can ever be will be 0. So we can say that a sub n is always greater than 0, and also it's a decreasing sequence, which is first term is 1. So if we plot the sequence on the plane, our first term is 1 and the sequence is decreasing and getting closer and closer to the 0, but never touches the 0. So it is bounded below by 0. Okay, in summary, we have learned that a sequence is bounded above whenever the a sub n is always less than or equal some number which we called it m. And also we have learned that a sequence is bounded below when the all terms of a sequence is greater than or equal some number which we called it n. In summary, a sequence in which all the terms are confined within a certain range, we call that sequence a bounded sequence. So a bounded sequence is a sequence which not only it has to be bounded above, but also it has to be bounded below. So we call a sequence bounded whenever all the terms of a sequence are confined within a certain range. For example, let's consider a sequence a sub n is equal to -1 to the power of n. We know that it oscillates between -1 and 1. For even n, we know that all the terms of the sequence is 1, and for the odd n, all the terms of the sequence is -1. If we plot this sequence on a plane, we can see that for 1, it equals to -1. When n is equal to 2, the value for the sequence is +1. When n equals to 3, it's -1. Whenever n equal to 4 is +1. So it's oscillate between -1 and +1. We can see that the sequence is confined between +1 and -1, which means that the sequence is bounded above and also is bounded below. So this sequence is a bounded sequence. Now, by understanding the definition of a monotonic and bounded sequences, we arrive at a theorem called the monotone convergence theorem. This theorem states that if a sequence is both monotonic and bounded, then it will converge to a limit, which means that if a sequence is monotonic, which means it's either increasing or decreasing, and it is bounded, which means that a sub n is confined between two numbers, which we called it n and m. Then the sequence a sub n converges to a limit, let's call it L. By using the theorem, let's examine that the sequence a sub n is equal to sine n is a convergent or divergent sequence. If we plot this sequence in a plane, we know that the sequence would be something like this. It is obvious that the sequence is bounded because it's bounded above by +1 and bounded below by -1. So the sequence a sub n is between -1 and 1. So it is bounded. Now, by using the theorem, the only things that we should check it is that this sequence is monotonic or not. We said that the sequence is monotonic sequence when it is either increasing or decreasing. But for this sequence, it is oscillating between -1 and 1, which means that sometimes it goes up and it's an increasing sequence, and sometimes it's a decreasing sequence. So it's not a monotonic sequence. According to this theorem, this sequence is not convergent because it's true that we proved that the sequence is bounded, but this sequence is not monotonic sequence. So we cannot conclude that the sequence is convergent. Because both of these conditions must be satisfied simultaneously in order to conclude that the sequence is convergent.